Good day, my name is George Melton and I'd like to talk to you about our patent and the technology behind it. First, we have to overcome a stumbling block, and that is perception. For example, when Mr. Nikola Tesla was in college, he proposed to his professor at the time, an engineering professor, I believe, Paschal is how you pronounce that. He proposed a brushless motor. The professor's response is, and I quote, "Mr. Tesla may accomplish great things, but he certainly will never do this. It would be equivalent to converting a steadily pulling force like that of gravity into a rotary effort. It is a perpetual motion scheme, an impossible idea." Well, as we all know, Mr. Tesla did go on to invent a brushless motor, an AC one, and I think AC current was the implication there. Today we can use magnetism in a rotary effort. So, how is it Darth Vader would say it? Today Professor Paschal's failure is complete. At some point, folks, if we want to use magnets to their full potential, we're going to have to get past some of our basic preconceived ideas that they're unusable. I've talked to some physics people about this idea. I had one fellow who was a physics teacher, he said, say to me that there is no more energy in a magnet than there is in a mailbox post. That first thing that went through my head was, well, if a mailbox post doesn't have any energy in it, then how's it holding up the mailbox? That aside, let's say if I set the mailbox post on fire, will it burn? Yes, it does burn. It emits light and heat and turns to ash. My mailbox post has energy in it. And I didn't take his criticisms after that too very seriously. I've had physics people say there is no energy in a magnet. And then I would say, well, explain to me then how it attracts things to it. And they said, well, it's force, not energy. And I realized at this point that this person was trying to tell me magnets are physically ineffective because of a name tag that humans have put on them. Okay. As I said, if we're ever going to use magnets to their full potential, there's some preconceived ideas that we're just going to have to get over. Instead, let's use our eyeballs and our common sense. Let's ask ourselves, let's go back to the really basics and say, is it possible for any magnet to impose a motive force of any kind on anything? If the answer to that is yes, then everything you're going to hear on this video is absolutely possible. At some point, we're just going to have to cut to the chase, and regardless of what names or tags you put on it, we're going to have to ask the question, did it move the ball or didn't it? Now, what I expect out of this is basically three different reactions. There are going to be some that still say, no, it's just not possible for a magnet to create or assist movement in any way. If you're one of those, you might as well stop watching this video right now. I've got nothing else for you. Now, there's going to be two other kinds of reactions. One is going to say, well, okay, the magnet moved the ball, but it shouldn't have. Then there's going to be the ones that were like me, that the first time they think of it, they're going to say, well, obviously, the magnet moved the ball. If you're any of the latter two, stick around. And let me show you how we can use magnetic flux to assist rotary motion. Okay guys, just a couple of quick things to go over. One is everything that you're going to hear and see on this video is protected by a United States patent. So we hope you like it, we hope you want it, but if you do, let's talk first. The second thing is also kind of a perception thing, but it's just to help you, the viewer. This idea is so easy and so simple. If you approach it like a Ivy League scientist, putting your hardest brain to it, you're going to way overthink it. It's really easy. Instead, approach it more like a fifth grader. Looking for a science fair project, figuring out a science fair project. That will help you pick up on it real quick, and there will be probably an aha moment here after a while, and all the lights will come on, and you'll pick it up easily, and you'll say, that's too easy. Wow, oh my God, that's too easy. He's hiding something. No, it's just really easy. So at first, just be open-minded, and don't try to think in math yet. At least for the first part, don't overthink it. It's really easy. Okay, let's do some fun stuff. Okay, so when we start talking about using magnets for movement in a rotary environment, there's basically two main problems you're going to have. The first, and most obvious, is that magnets don't like movement. They like to attract things to them and keep them there. That's pretty much it. Your second problem is going to be the shape of the flux. Now, I know we've all seen the diagrams of how the flux flows from the North Pole to the South Pole. In practice and in the field, it is North Pole until it is South Pole. And what that means is, when you look at the flux as a whole, it's a perfect circle. I mean, absolute perfect sphere. Absolutely perfect. So trying to get more than one of these things to assist one another's movements is kind of like trying to get beach balls to help one another move in a straight line. It's insanely crazy. It doesn't want to do that. So there's your two main problems. It's steady on, you can't turn it off, and then the shape of the flux is your other problem. Okay, so to address your first problem is easier than the second. Really, all you have to do is make sure that everything is fastened or attached so that it stays where it's supposed to be or in its orbit. The second thing is, when it's in motion, you have to be sure that your proportions are right. Okay? And what I mean by that is, the field of your magnetic strength and what you're imposing on this turning axle cannot be stronger than the momentum of the turning, or it will want to hold it in one spot. So you want to use the momentum to your advantage, so that means your magneticism needs to be in proportion with the inertia of the shaft. Okay? That's it. Nail it down and get your proportions right. That's how you deal with the first problem. The second problem is, well, to address it, we're going to do what humans do best. We're going to take something that was made perfect and we're going to make it imperfect so that we can use it. Here's how. Okay, to deal with our perfect flux shape, what we'll do is we'll reshape it. And we'll do that in two ways. We'll do that by combining fluxes, and we'll do that by bending fluxes. Then we'll contain the shape that we've made, and then we will make sure that all of our parts have a prefabricated path, if you will, to follow, so that everything reacts in the way that you want it to react, rather than the way it would react naturally. First off, if you combine two magnets together, their flux fields combine. This magnet is now stronger on this end than it is on this end. And that will make the flux look something like this. Next, we'll bend the flux. And the way we'll do that is by using like poles. Just as you can combine flux fields of unlike poles, like poles do not combine. No two like poles, fluxes, can exist in the same space at the same time. So right now, these fluxes are not round, they're flat in the middle because I've matched them together. And we can use that principle to create a path for our receiver that we will make in a moment. Okay, so we can use simple ferrous steel to contain excess magnetic flux, like so. Like water, magnetic flux follows the path of least resistance. In this case, the steel is an easier course for it to follow than the air. Unlike water, however, magnetism is a quantum principle and does not flow. Magnetism does not flow from the North Pole to the South Pole, it simply is. That's one of the things that makes it really good for high RPM applications, because there's no lag time. At any rate, the magnetic flux now is mostly on this side, is mostly contained by the steel. There will be a little drift, but not enough to be concerned with. So that's how we contain it. Now here's what's going to happen. We're going to make a driver that sits on the outside of the rotating shaft, and it is stationary. Then we're going to have a receiver that attaches to the shaft that actually receives the magnetic pull from the drivers. Okay? So this is an example of a driver block that we could make. Here you see the magnets combined like we did before for our combination reshaping. And here you see them opposing on a block. These are like poles facing out, so they can't occupy the same space. That means there's a little tiny slit in between them. And what that will do is allow the ball part of the receiver to slide through there without trying to get stuck in one spot. Here is an example of a receiver set I made for a previous experiment that involved an electrical generator. Some of you might have seen that. It's a ball. You'll want to use something round. There's no flat surface. There's no opposing side. Now these are steel balls, and they have a magnet attached to them on this back side, so that the pole I want faces this way and attracts to the drivers set out here. Now here's the magic of this whole thing. You can see the flux from this driver side, well, this side of the driver, and the flux from this side of the driver acting upon the receiver. You can also see the schism that we've created by facing like poles out. So these fluxes don't combine, they oppose one another and create a tiny rift in the middle. That's where our ball goes through, and that's why we want it to be round, so that there is no opposing sides. Nothing is flat against anything, and that will keep it from being stuck in one spot. Here we have the flux contained by the plain steel that I described earlier. There's also a magnet here that lends to the attraction to this part. As you can see, as the receiver follows its path, its orbit, the first part of the driver is the strongest, as you see here by the flux drawings. As it gets later, it starts to pull away, but it doesn't have to pull away from this. It has to pull away from that. So as a base number, without any combination of other drivers, your gained advantage is going to be the difference between this and that. Ideally, you would use several of these drivers and several receivers, like this. Optimally, you would have another driver set in a different space than this driver set turned, so that when your receiver gets to about here, a different driver starts this pull from another position. So see, easy. It's easy. The magnets I used and the drawings I used are examples. This technology is very scalable and can be used on any size machine. So just to wrap it up, to use magnets in a rotary environment, we first have to make the flux field imperfect. We do that by combining fluxes and by bending fluxes. Then we contain the flux that we've made, the flux shape that we've made, and we create a path for the receiver. Thank you.